I scream, you scream, we all scream for ice cream. In Lab 8, Experiment 3, we're taking a look at the chemistry of ice cream. There are two important concepts we want to look at. First is the conservation of energy, and the second is the concept of colligative properties. Everybody loves the law of conservation of energy. It simply says that energy can be neither created nor destroyed. In other words, all the energy that ever was and ever will be is currently in existence. Now, just because you can't create or destroy energy doesn't mean you can't do a lot of fun things with it. For example, energy can be transformed and energy can be transferred. Let's take something really simple, like boiling some water. When you want to boil some water, you turn on your stove. And just the act of turning on your stove is a transformation of energy. After all, you're taking electrical energy and you're transforming it into the form of energy known as heat. Well, what's that heat doing? That heat is going into the water. And remember, water is actually a collection of molecules. And those molecules are attracted to each other by intermolecular forces. That heat energy goes into breaking the bonds, those intermolecular forces. It goes into breaking those intermolecular forces between the water molecules. It breaks the force of attraction for the water molecules and gives the water molecules what's known as kinetic energy. When the water molecule gains enough kinetic energy, it leaves all the other water molecules behind and enters the gas phase as steam. And steam is simply water molecules with enough kinetic energy that they don't have any attraction for any other water molecules. Kinetic energy, by the way, in case you didn't know, is the energy of motion. Oh! So if we just look at the simple act of boiling water, we've transformed electrical energy to heat energy, using it to overcome intermolecular forces, and become kinetic energy. So we can definitely transform energy from one form to another. Not only that, we can transfer energy. Now, this seems like a simple enough concept. I have 100 milliliters of water at 20 degrees Celsius, and then I have, pictures not to scale, 100 milliliters of water at 40 degrees Celsius. In other words, I have 100 milliliters of hot water and 100 milliliters of room temperature water. What happens if I mix those two glasses of water together? Well, you know, if you add hot water to cold water, the cold water gets hotter and the hot water gets colder. And you wind up with 200 milliliters of water at the same temperature. This is a concept known as two objects in contact with each other will transfer energy in the form of heat. Until they arrive at the same temperature. Thermodynamic equilibrium is the concept that two objects in contact will transfer heat until they arrive at the same temperature. Now, here's something that you may have run into before. Cold doesn't exist. There's no energy known as cold. Cold is simply the absence of heat. So something can't transfer cold. What has to happen is, in order for two objects to arrive at thermodynamic equilibrium, heat has to leave the hotter object and enter to the colder object. My wife will complain about my cold feet in bed, and she'll say, "I can feel the cold coming off your heat." And I always tell her, "You are so wrong. You don't feel my cold feet. You feel the heat leaving your feet." For some reason, this does not give her comfort. So, two objects in contact will eventually reach thermodynamic equilibrium, meaning that they will eventually arrive at the same temperature. The concept of thermodynamic equilibrium is really, and the concept of transformation of energy is really important when it comes to making ice cream. If we want to make ice cream, we have a problem. We have a bunch of milk in a container, and we somehow need to get heat to leave the container. We have to get that heat to leave the milk. In other words, in order to cool something, we have to get it to remove some of its heat. So we have to do one of two things. We either have to place an object on the outside that is colder than the milk, or we have to use the milk as the source of energy for work. After all, one thing we didn't do here is we didn't define what work is. We didn't define what work. We didn't define what energy is. Energy is the stored capacity to do work. Or energy is the, simply put, the ability to do work. And if you're like me, you know that if you have low energy, you don't have the ability to do a lot of work. But if you're high energy, you've got a lot of ability to do work. So energy, simply put, is the ability to do work. So let's think about how ice cream is traditionally made. If you've ever made ice cream before, you know you take your milk, and you place it in a container full of ice. You know that the ice is colder than the milk. So right away, you know that some of the energy from the milk is going to go into raising the temperature of the ice. But ice also melts, right? melting requires energy. Ice Ice is what is known as a molecular crystal. In an ionic compound, we know about crystals, and we know that every point in a crystal is an anion or a cation. In a molecular crystal, instead of the points in the crystal, or the repeated pattern in the crystal being made up of anions and cations, the repeating pattern is made up of water molecules. In other words, you have a repeating pattern of water molecules. And this is a very ordered pattern. The pattern's repeated. And the molecules of water are held in place by intermolecular forces. Specifically, if you think back to our previous talk, they're held in place by hydrogen bonding. The water molecules are attracted to each other, right? Think about when you're first dating somebody. You're so attracted to them. And it takes all your willpower to tear yourself away from them. You hang up first. No, you hang up first. No, you hang up first. You hang up first. Sorry. But you know, it takes a lot of energy for them to tear themselves apart. It actually does take a lot of work and energy for them to tear themselves apart. Same way for these water molecules. If we want the water molecules to overcome that intermolecular force so that they can move around a little bit and form a liquid, it's going to require the input of energy. And that energy is often in the form of heat. But it requires energy Matter of fact, the amount of energy it takes to melt ice is given a very fancy name. It's referred to as the heat of fusion. Fancy word, huh? And that's the amount of energy it takes to melt the ice. All right, so let's apply this to our ice cream example again. I've got my container. Oh, I should use the blue Star Wars milk, shouldn't I? Hey, everybody write down Star Wars. Everybody write down Star Wars. Everybody write down Star Wars. I hope everybody's writing down Star Wars. Thank you, everybody who wrote down Star Wars. All right, so I have my milk, which isn't blue like it is on Tatooine. And my milk's container is placed in some ice. And I have heat leaving my milk in order to do two things. In order to melt my ice and to raise the temperature of the ice. Now, if we just placed the milk in a container of ice, the milk would simply melt enough ice until it established thermal equilibrium with water, with the new ice water, which would probably be around 0 degrees. But we want to get our milk cold, really, really cold. In other words, we want to make sure that something causes the milk to lose even more heat than's necessary just to establish thermal equilibrium and just to melt what ice is necessary to establish thermal equilibrium. And that's where the salt comes in. If you've ever made ice before, you know that part of the procedure is you add salt. Then no, you don't add salt to the milk, you add salt to the ice. Well, you know from simple observation that whenever it snows, salt is sprinkled on the roads in order to help make the ice on the roads melt. So you know intrinsically that salt causes ice to melt. But that's really not a good way to think of it. I'd like to think of it a different way. I like to say that salt really prevents what salt really does is it prevents water from freezing. In order for water to form ice, our water molecules have to form a crystal. And we've already said that crystal is a nice ordered, repeated pattern. In other words, those water molecules have to line up and get into position in just the right place. Well, when you place salt into water, what you're doing is you're releasing sodium ions and chloride ions, and we've already been through an electrolyte lecture and how when you place an ionic compound in water, the ions break up into their individual ions. So when you place salt in water, you produce sodium and chloride, and those ions are floating around in the water. Well, what happens to those ions of sodium and chlorine in the water when the water forms ice? We know that if you get it cold enough, salt water can freeze. Right? All you have to do is turn on the nature channel, and you'll see all sorts of pictures of icebergs, frozen salt water. So salt water can still freeze, but there must be something that prevents the water crystal from forming easily, causing the water to form ice at a lower temperature. Well, what happens is, in order for ice to form in salt water, a place has to be found for the sodium and the chlorine inside the ice crystal. You can think of it this way. You have two water molecules. And these two water molecules, they're in love. They want to get together and they want to form a crystal. However, just as they're getting ready to go out on a date, hey, mind if I tag along? A sodium ion drops in, right? And you can't do anything with a third wheel on a date. Same way for the water molecules. The water molecules are trying to maneuver themselves to get around so that they can form a crystal. But what happens? Where they look, there's a sodium or a chloride preventing them from easily forming that water crystal. What you have is you actually have a physical blocking of the crystal formation. Whenever you dissolve anything, whenever you dissolve anything in water, it lowers the freezing point. This is known as anytime you dissolve anything in water, anything dissolved, sorry, I'm correcting my grammar here, anything dissolved in water lowers the freezing point. This is known as a colligative property of water. We always think of salt as lowering it, but it doesn't have to be salt. You could try it with ethanol, right? Don't believe me, those of you over 21 with legal access to alcohol, try sticking a little bit of your favorite adult beverage in a plastic container, please, in your freezer and see what happens. Unless your freezer is up really, really high, you're probably not going to freeze it, especially if it's a hard alcohol. You might get your beer or your wine to freeze, but you're not going to get vodka to freeze, right? Or tequila, or something with a really high ethanol content. Anything dissolved in water lowers the freezing point. So salt water will freeze is much, much lower than the freezing point of pure water. So what happens when you add salt to that ice around your milk? All right, so we have our milk again, and our milk's in our pitcher of ice. Now, if it was just going to reach thermodynamic equilibrium, our milk would eventually reach a temperature that was the same as what would be an ice-water mixture on the outside here. But we want our milk even colder. We can do that by forcing the ice to melt. We place some salt onto the ice. Well, the presence of that salt forces the ice to melt. It lowers the freezing temperature of the water. Well, we know, since the salt forces the ice to melt, and we know that melting requires energy. And energy can't be created or destroyed. So if the salt is forcing the ice to melt, where's the energy going to come from? Well, for the ice in this part of the container, it might come from the air. But for the ice in this part of the container, what's right next to it? what's right next to it that it could steal energy from? The milk! Right? And that's exactly what happens. Because the salt lowers the energy of the ice, forcing the ice to melt, that forces the ice the ice to take some energy from the milk, lowering the temperature of the milk even further. Now, eventually, once that ice all the ice that's going to melts due to the addition of the salt, yeah, you're in thermal equilibrium again, but you're in a thermal equilibrium now that's well below zero. How big an effect can this have? Well, the amount of the effect actually depends upon the amount of ice you add. The more ice you add, the lower the freezing point of the salt water. And that's a characteristic of a colligative property. A colligative property is a property that depends only on the amount of solute and not the identity of the solute. In other words, like we said, freezing point lowering is an example of colligative properties. And the more solute you have, the lower the freezing point temperature. In other words, the more salt you add to water, the lower the freezing point of that salt water it is, because the harder it is for those two water molecules to finally get together. Now, interestingly enough, the colligative property for boiling point's the exact opposite. Again, just think of the kitchen. Ooh, and you guys should write down Aunt Beru. Why don't you write down Aunt Beru? After all, she was in the kitchen serving Luke the blue milk. All right. Another colligative property of water is boiling point elevation. When you cook and boil spaghetti, you add salt. One of the reasons you add the salt, in addition to taste, is by adding the salt, you actually raise the boiling point of water. Meaning that if you add enough salt to water, the water will actually boil higher than 100 degrees Celsius. So you can get your water much hotter and boil your spaghetti a lot faster. Why does this work? Why does the addition of salt increase the boiling point? And it really has to do with what the definition of boiling point is. The boiling point of a substance occurs when the vapor pressure of a gas, or the vapor pressure of the liquid, is equal to atmospheric pressure. What's the vapor pressure? Vapor pressure is a way of measuring the amount of gas molecules right above the surface of a liquid. So I've got my bucket of water here, and right above the surface I have a bunch of water molecules in the gas form leaving the liquid and pressing out, right? They're pressing out and up, pressing up and away from the water with a force or with a pressure. And you have water molecules, and you have air molecules pressing back down. When the pressure exerted by those water molecules in gas form gas or steam here, when the pressure of the water gas equals the pressure of the atmosphere, you're said to be at the substance's boiling point. Okay, so how does the presence of salt interfere with this process? Well, in order for water to enter the gas phase, the water molecule has to leave the surface of the liquid. And if you have just pure water here and you look at the surface of the water, you have a bunch of gas. You have a bunch of water molecules, and those water molecules can launch from whatever point on the water's surface they want to. Now, if you add salt to your water, well, in a solution, particles are evenly distributed. So at the surface of your water, where you used to have pure water, some of those water molecule exit lanes are now replaced by sodium ions or chloride ions. In other words, the water molecules can't get out. It's kind of like being on a busy road and coming to a bunch of toll booths, and in a pure liquid, all the toll booths are open. But in a liquid that has a solute in it, some of the exit ramps are blocked by salt. In other words, some of the toll booths are closed, so the cars can't exit as rapidly. Since the cars can't exit as rapidly, it takes much longer time and much more energy for the gas above the liquid to build up and to equal the pressure of the atmosphere. So once again, the salt is physically interfering with the water entering the gas phase. The salt is physically interfering with the water's entrance to the gas phase. All right, a quick reminder. If you make ice cream, you do so at your own risk. And all chemistry should be done wearing chemical splash goggles. Please write down, what else? Blue milk.